So we found approximations for the Nusselt number and the boundary layer thickness, right? Let me go back, those are very important. We found that on page 1, for Prandtl number much less than 1, we found that the Nusselt number scales with the square root of the Reynolds number and the square root of the Prandtl number, and the proportionality constant was approximately 0.53, which is given by the polynomial, third order polynomial approximation. And we said that this is in lines with our earlier guess from the scaling analysis, right? We were expecting Nusselt number to be proportional to the square root of the Reynolds number and the square root of the Prandtl number, right? And so that means like scaling analysis did a great job on that. And the other thing is that for Prandtl number much larger than 1, we found that Nusselt number scales with the square root of the Reynolds number times the 1/3, 1/3 power of the Prandtl number, which is pretty, and the scale, the proportionality constant we found from the approximation, and this is like miraculously the same as this result, right? For Prandtl number much larger than 1, we were expecting exactly Nusselt number scaling with Prandtl number to the power 1/3. Okay. Now, let me ask you the following question. Now, if you have a faith in these relations, like these summarized relations, which are from the scaling laws, but not from like the model, right? Do we really need to do all these things? Do we really need like do all these things and find this Nusselt number, like this proportionality constant and so on? What do you think? Or should we be still okay with the Nusselt number like proportional to the Reynolds number to the power 1/3 and Prandtl number to the 1/3? What do you think? Another way of asking this question is this relation as helpful or as useful as this relation? What do you think? No answer. So to me, this equation and this equation are equally useful. The reason is the following. When you already know how the Nusselt number scales with Reynolds and Prandtl number, you can just do experiments to find out like this proportionality constant. You just plot the Nusselt number as a function of Reynolds number and Prandtl number, and then you find out what is that proportionality constant. And it's going to be an experimental value. It's still going to be more accurate than 0.22 because that way you're going to find out a value that what the experiments tell you, what the nature tells you, rather than your idealized approximations and so on. So knowing that the Nusselt number scaling with the Reynolds to the power 1/2 and Prandtl number to the 1/3 is already a fantastic job here that we did using the scaling analysis, right? So I actually ask everybody to appreciate these equations. Okay. So Any questions so far? Okay. Now let's go back to the heat exchanger design. We talked about, as you said, the types of heat exchangers. We talked about like what we're gonna learn. We talked about different designs of heat exchangers with different flow arrangements, co-current and counter-current. We actually pointed out some surprising facts about them, especially for the counter-current. We said the outlet cold temperature might be larger than the outlet hot temperature, which was something very important. And for the co-current arrangement, we said that the temperatures asymptotically approach each other, and the difference get close to each other actually each time. And you need like an infinitely longer heat exchanger for the co-current arrangement to get the hot and cold streams to get the same temperature. Whereas with the counter-current arrangement, you can have it with a finite size. One thing that I didn't mention was this is from chapter 22. Oops. This is from chapter 22 in textbook, so it relates to chapter 22 for those who wants to have a look. Okay, so those are the things we discussed so far. We didn't actually delve much into details so far, so now we're gonna try to design or model the heat exchangers, right? And the first thing I would like to start with is a very important concept which is going to be useful in designing heat exchangers, which we had talked about to some extent, but let's talk about it in more details. It's called the concept of overall heat transfer coefficient. Overall heat transfer coefficient. Okay, so imagine you have a fluid here flowing in this direction, and there's going to be another fluid, but a solid layer separates them, like in the case of a heat exchanger. Another fluid flowing in this direction. This is the T fluid 1. This is the T fluid 2. And heat is being transferred from the hot fluid to the cold fluid. Imagine that this one is the hot fluid. So this is the direction of the heat transfer Q. And let's just imagine TF1 is larger than TF2. Okay. And imagine that this is a pipe, like this is like part of a pipe. So you can just think of this slab as just the thin layer of the pipe. Okay, that's the skin of the pipe you can think of. Okay. And imagine that this is the axial direction. Or center line. Center of cylindrical pipe. Okay. And imagine that this is the inner radius of the pipe, Ri, and this one is the outer radius of the pipe, R out. And suppose there is heat transfer coefficient Hi inside and heat transfer coefficient Ho outside, and the conductivity of the material is K, of the pipe material. is K. Okay, so this is our system and labeling. And from our earlier notes, we actually talked about the resistances, right? We said that the heat transfer rate, Q, is equal to the temperature difference, which is the TF1 minus TF2 for this case, divided by the resistances, the sum of all the resistances. The resistance corresponding to the inner side, the pipe's inner heat transfer coefficient is 1 over HIAI, right? If you do the shell balance and do all the analysis that we had done so far, you're gonna find that the resistance corresponding to the inner convective heat transfer is 1 over HIAI plus the resistance of the pipe, resistance to heat transfer through the pipe, is the logarithm of R0 over Ri divided by 2 pi KL. I mean, this is from your, I mean, you can, you probably have already figured this out in the homeworks, where you have a cylindrical geometry where there is no heat generation. You see that the ratio between the temperature differences and the Q heat transfer rate equals the logarithm of the radiuses, logarithm of the ratio of the radiuses divided by some 2 pi conductivity times length, okay, plus the outer heat transfer resistance, which is 1 over H out, A out. Now, A in and A out might not be necessarily equal to each other. If it's a negligibly thin pipe, you can assume AI is equal to A0, but generally we don't assume it. Okay, so we say that from the earlier part of the course. Okay, this is the convective heat transfer resistance for the inner fluid. This is the convective heat transfer resistance for the outer fluid. And this is the conductive heat transfer resistance. Conductive heat transfer resistance. Okay. And we said that there's a quantity, like a convenient quantity that you can define, which is called overall heat transfer coefficient, which is shown as U. Overall heat transfer coefficient defined such that Q is equal to U times A times T fluid 1 minus T fluid 2. Like in sense, we said that the overall heat transfer coefficient looks like the H in the Newton's law of cooling. Basically, it's the Newton's law of cooling, which is written based on the difference of the terminal temperatures. But unlike the Newton's law of cooling, where you have H here, the differences correspond to the two fluid temperature differences. Not one of them is fluid, the other one is solid. So, okay. And the area is a little ambiguous because you can actually argue that there are two different areas. So which one are you going to use? You can use whichever you like. Let's call it the reference area, a ref, but you should actually declare which one you're going to use. Okay, so this we say can be either outer or inner surface area. If this is inner, U corresponds to the inner heat transfer coefficient. If that's outer, U corresponds to the outer overall heat transfer coefficient. Okay. So you can say 1 over U A reference is equal to 1 over U0 A0. You can do it U0 A0. If you use A0, the U that you get is the U0, which is the overall heat transfer coefficient defined from the outer area, is equal to 1 over. You can also say, let me take my reference as the inner area. Then your U is defined as the UI. And they're all equal to the sum of the resistances, right? This denominator. So I'm going to write down that denominator, 1 over HIAI plus logarithm of R0 over Ri, R out over Ri, divided by 2 pi KL plus 1 over H0 A0. Okay. So let's actually talk a little bit about this. Let's actually think about different scenarios. For a very thin tube, what happens to logarithm of R0 over Ri? Well, R0 over Ri goes to 1, so logarithm of 1 goes to 0. So this goes to 0. And what does it mean? The conductive resistance could be neglected, right? In that case. Another scenario is there can be like additions to this. There can be more than these 3 resistances in the case where you have like scaling, for example, deposition of some particles on your heat exchanger, because as you use heat exchangers in the industry, you're going to learn later that probably in design courses, they're going to come with they're going to age, and because they can actually get rust, they can get like impurities, so you can have like layers which is scaling on the surface of the pipes. You can have some deposition. So let's try it. There can be deposition of scales, minerals, or dirt with time. Or they can simply get rusted, and the conductivity can change, because you know that the metals are good conductors, but when they rust, they become poor conductors. In the heat exchanger. And this adds to the heat transfer resistance. And a good way to model this is to use what's called as a fouling factor. And it's we're going to use R for the resistance, F for the fouling, and this is called fouling factor is equal to 1 over sorry, U dirty, the one with like scaling layers, right? Minus 1 over U clean. Well, actually, 1 over U clean corresponds to this original heat exchanger, the clean one. But for the dirty one, you should get larger value. And the difference between the two is the fouling factor. So you should add it or take it into account during your design. Okay. So in words, R represents how much higher the heat transfer resistance is, right? R F represents how much higher the heat transfer resistance in the presence of deposits is than the case without, compared to the case without any deposits. Any deposits, meaning that freshly new, brand new heat exchanger. Right? So this is the difference between the used heat exchanger versus brand new heat exchanger. You should always take it into account. Okay. So 1 over U dirty A0 is your heat transfer resistance, overall heat transfer resistance, is equal to 1 over HIAI. I'm going to sum over all the resistances, okay? And you can actually say that the fouling can be both inside and outside, so you can actually add the RF terms for the inside and outside. So RF I divided by AI, okay? If you have a look at this formula, you will see that if you only divide by area, you get the resistance here. So, I mean, because you should have the area here to make it resistances, right? So you should divide both sides by area. And if you divide by area, you get the fouling factor divided by area as the resistance. Okay. Plus the conductive resistance divided by 2 pi KL plus the outer fouling RF out divided by A out plus 1 over H0A0. Okay, so we call this internal fouling. And we call this external fouling. It's nothing but, let me show it on the picture. Brown. Okay, so let's see. So imagine that you have just rusty layers building up here. Okay, that corresponds to those, or maybe that's food depositing. Especially in the food industry, you have this fouling pretty much pronounced. Okay. So far, we have assumed that there is only one value for TF1 and TF2, right? Only one value for TF1 and one value for TF2, right? That's in other words, the fluid temperature here is the same as fluid temperature here, and so on. We just care about what's happening in this direction. We didn't care about actually what's happening in this direction, right? But when you model heat exchangers, the stream is going to change its temperature, so you need to find a good way to model that, right? And in that case, like in the previous cases, we had this like Q is equal to UA delta T, right, in our analysis so far. And we basically know these delta T's, right? You know the areas, and you can calculate the Q from our previous analysis. But for this case, for this particular case, we know this Q, right? So you can say, okay, imagine I know how much heat should be or must be transported from one side to another if I know, for example, the duty of the heat exchanger that I would like to design. And you can come up with the area, and you can say, okay, let's assume we know this. But at least what it means, right? But delta T, I mean, what does this delta T correspond to, right? It's going to change throughout the heat exchanger, right? So we need to find out the relevant delta T that what the relevant delta T is. Okay, our analysis is gonna show that it's a temperature difference which can be described using what's called as logarithmic mean average. Logarithmic mean temperature difference, I'm sorry. And today's class, we're actually gonna try to show why it is so, and why the temperature difference should take this form. Okay. So let us have a look at what this delta T is. What this delta T must be. Okay. Now let's start with a simple analysis, which is the energy balance. The Q, the heat transferred from the hot fluid to the cold fluid, is equal to the heat lost by the hot fluid, right? And you can use the MCP delta T, right? And you can say the flow rate, the mass flow rate of the hot fluid per unit time times the heat capacity of the hot fluid times the temperature difference of the hot fluid, which is the inlet temperature minus the outlet temperature. So this is how much heat the hot stream is losing, right? So this is heat lost by hot fluid. Okay. You can also say that, or that must be equal to how much the cold fluid actually gained heat. So MC, the mass flow rate of the cold stream, times the heat capacity of the cold stream times the temperature difference in the cold stream, TC2 minus TC1. So I want to take it, I want to attribute a positive value for this, and I know that the TC2 is larger than TC1. That's why I actually wrote this way instead of the other way around, because I know that the TC2 is larger than TC1, unlike the TH1 and TH2 relation. And this is the heat gained by cold fluid. Okay. So let's write down what each thing means. Q is the heat transfer rate, the amount of heat transferred per unit time. It's also called total heat duty. Of the heat exchanger. MH dot is the flow rate, mass flow rate of the hot fluid. Well, actually, if it's like volume flow rate, then the C should correspond to volumetric heat capacity per unit meter cube. But generally, the heat capacities are defined in terms of per unit masses. Or if it's molar flow rate, then that would be molar specific heat capacity. So the CH is the specific heat capacity of the hot fluid. TH1 is the inlet temperature. Inlet temperature of the hot stream, hot fluid. TH2 is the inlet temperature of the, oh, sorry, that's the outlet. Hot fluid. Similarly, MC dot is the mass flow rate of cold fluid. C is the specific heat capacity of the cold fluid, and the TC2 start with, yeah, TC. Let's start with TC1 is the inlet temperature of the cold fluid. TC2 is the outlet temperature of the cold fluid. Okay, so far so good. We wrote down our energy balance and we described all terms there. But how is that going to be useful, right? I mean, what are we going to do with that? If, for example, imagine you know like these streams, right? So you know like what is the flow rate, what is the heat capacity. I mean, just knowing the name of the fluid and the temperatures corresponding, you can know you can look for the heat capacities and so on. So if you knew, for example, 3 of the 4 temperatures, you can solve for the other one, right? Yeah, the fourth one can be calculated. So let's write it, because that's an important observation. If 3 of the 4 temperatures are known, the fourth can be calculated. The unknown one can be calculated. Using the energy balance above. That's one observation. Now let's proceed. Let's proceed. So let's go back to our Q is equal to UA delta T equation, right? Suppose we know the heat load. Because that's generally the case, because when you actually design a heat exchanger, the first thing you know is from what temperature to what temperature you're going to decrease the hot fluid, or from what temperature to what temperature you're going to increase the cold fluid. So that's generally, that's what's known already. So you can take it as granted that Q is known, okay? And the U, we know the U, right? We know U because have a look at this equation. By knowing the pipe material and by knowing the flow conditions, you can estimate those, as we have seen earlier. So with a particular architecture or like setup, for example, and also the material selection, you basically know U. For example, if you pick like steel pipe at a certain diameter, 2 fluids surrounded, one is air, one is water, for example, you know the Prandtl numbers. If you know the corresponding flow conditions, you can have a rough idea about the Nusselt number, and then you can get the H, the heat transfer coefficient for both sides, and then you can calculate the overall heat transfer coefficients. Okay. This is from thermal properties and correlations, like the Reynolds analogy or other correlations that you can use to estimate the Nusselt number, and from there the H. Okay, so but what about this again? So we know, we don't know that term, but we know what temperatures we are designing for. But not, yeah, what delta T we should use. What I mean is the following. What I mean is the following. If you have temperature variation along the longitudinal direction, and imagine this is your hot stream, your cold stream. This is TC1, this is TC2. Imagine co-current arrangement. T hat 1, T hat 2. Okay. Now, what I mean by delta T is the following. Am I going to use this delta T, or this delta T, or this difference? Which difference am I going to use? So, for example, I can have like 50 degrees difference here, but I can have maybe 20 degrees difference, or maybe 10 degrees difference here. So which delta T am I going to use? That's my question. Or is there any average that I can actually take? So that's the tricky question. So this is let's focus on the co-current flow heat exchanger design. Okay, let's focus on this one before making things more complicated. Okay, so let's go with the thermal energy balance. Okay. And where am I going to do this thermal energy balance? Since I know that the temperature differences are different everywhere, I'm going to pick an arbitrary one like we did in the shell balance, right? So I'm going to pick a small shell here. Let's pick this one. Let's pick a shell and make a shell balance. And imagine that this is the Q transferring from the hot to the cold. Okay. And imagine that there is this much of change in the hot temperature. Let's call it dT hot. And similarly, there is this much of a change in the cold temperature, and let's call it dT cold. Okay. And because of this Q transfer, there is this much of temperature difference in the hot, and there is this much of gain in the cold temperature. Right? Now I'm going to do the energy balance for this. dQ, let's call this infinitesimal Q transfer as dQ, not Q, the total Q, but it's just the Q corresponding to the infinitesimal shell. Sorry. That's equal to the amount of heat transferred from the hot to the cold, which is the m dot h times C hot times the change in the temperature, change in the temperature of the hot. Now, since the hot temperature is decreasing, dH is negative. So if I want to take a positive value, I want to make it minus dTH. Okay, I want to find out a positive value for this. Okay. Similarly, the amount of heat gained by the cold is m dot C times Cc times the amount of temperature change, dTc. Since dTc is positive because as you go to the right, TCs are increasing, so dT is positive. Okay, so that's the differential equation. Let's integrate this. If you integrate this, what do you get? Will give the following. If you integrate the leftmost side, dq, it's just the q, right? The total heat transfer is equal to m dot h, constant along the stream, ch, imagine it's constant along the stream, times T hat 1 minus T hat cold. T hat 1 minus T hat 2. It's because basically you're calculating from boundaries 1 to 2, right? And yeah, so we're calculating from 1 to 2. So it must be t hat 2 minus t hat 1, but there's also a minus sign, so that makes it the other way around. Is equal to mc dot, similarly, cc, t cold 2, t cold minus t cold 1 this time. Were it not for this minus, it would be the other way around, because we are integrating from 1 to 2. So it should be final minus initial. It should give us the, I mean, and this makes sense, right? I mean, integrating this should give you the equation you already know, this one. That makes sense. But let's do something else in here. Let's relate how much of a change that the T hat, sorry, yeah, how much of a change you have in the temperature of the hut infinitesimally to the amount of heat transfer. So let's relate this thing to this thing. So dT hot is equal to minus dq divided by m hot, m dot hot times c hot. Similarly, dT cold is equal to dq divided by m dot c cc. Okay. And how am I going to make use of it? I want to get the temperature differences. I want to get how much of a temperature difference between these two things I have. So, in other words, I want to get this temperature difference. Is that clear? So, one thing that I can do, I can get the infinitesimal form of it by subtracting this one from this one. Okay, so let's do it. dT hot minus dT cold is equal to minus dq times 1 over m hot dot c hot minus 1 over m cold dot c cold, if you subtract. Okay. Or, I mean, this is, you can also write it as the temperature differences, T hot minus Tc minus dq over m hot dot c hot minus 1 over mc dot cc. Okay. And let's call this equation 1. Okay. But how am I going to make use of this temperature difference? Here is how. You can relate this temperature difference to the amount of heat transferred, because if you know the overall heat transfer coefficient, it's just the proportionality constant, right? The heat transfer coefficient times area is the proportionality constant between dq and the temperature differences. So you can say dq is equal to that infinitesimal heat transfer rate is equal to u times the infinitesimal area that corresponds to that particular segment times the temperature differences, T hot minus T cold at that segment, right? And if we substitute this to equation 1, gives d T hot minus T cold is equal to minus, instead of dq, u dA 1 over m hot dot C hot minus 1 over m cold dot C cold times T hot minus Tc, correct? So I plugged in these here. Okay, any questions so far? Now that I have the temperature differences in this equation, I can collect them on one side, on the same side, and you get d T hot minus T cold divided by the same T hot minus T cold is equal to minus U 1 over M hot dot C hot minus 1 over M cold dot C cold, okay, and dA, right? And you can integrate this because this is something like dx over dx, right? You can easily integrate it from inlet to outlet. There is no ambiguity between the inlet and outlet because this is co-current. So the inlet of the hot is the same as the inlet of the cold. Inlet, outlet. Okay. And you get the logarithm of the temperature difference T hot minus T cold in the outlet, T hot 2, T cold 2, divided by the temperature difference, again, T hot minus T cold, but in the inlet on the left-hand side. On the right-hand side, you have, you can think of this constant, this constant, this constant throughout the entire heat exchanger. So you have negative U 1 over M hot dot C hot minus 1 over M cold dot C cold. And the integral of dA is the total surface area, right? Area of the surface area of the heat exchanger, right? What about these terms? So you can have a sense of these terms from the overall energy balance, right? From overall energy balances. Have a look at this. Let's see, where is it? Yeah, there you go. So you can get this thing with respect to Q and the temperature difference. So let's do it. And similarly, this one as a function of this and this, right? So you can say 1 over M hot dot C hot is T hot 1 minus T hot 2 divided by Q, and 1 over M cold dot C cold is equal to T cold 2 minus T cold 1 divided by Q. Let's plug them in to get logarithm of T hot 2 minus T cold 2 divided by T hot 1 minus T cold 1 is equal to minus U T hot 1 minus T hot 2 divided by Q minus T cold 2 minus T cold 1 divided by Q. Or you can just combine these and subtract this because you have the same denominator, right? So this equals negative. By the way, you have A here, I forgot. right? Negative UA over Q, some temperature differences. You can call it as T. Let's write it down. T hat 1 minus T hat 1 minus T cold 2. Okay, let's see. T hat 1 minus T hat 2 minus T cold 2 plus T cold 1. Correct? Let's check it again. Okay, T hat 1 minus T hat 2 minus I guess I made some like sign mistakes somewhere. Oh, yeah. Oh no. Oh, okay. So here you go. When you subtract this from this, you should get both negative. So this should be plus. That's a correction. This should be plus. Okay. And here this must be plus, and this must be plus. This is plus. And so we have this plus. Okay, good. And so this must be plus. This must be minus. There you go. Okay, good. And from here you get UA over Q. Let's distribute negative to get so this becomes T hat 2 plus T hat 2 minus T cold 2, right? Minus T hot 1 minus T cold 1. If you check, this should be the right answer. Okay, and now you can solve for Q, right? And Q becomes equal to U times A T hot 2 minus T cold 2 minus T hot 1 minus T cold 1 divided by logarithm of this thing, T hot 2 minus T cold 2 divided by T hot 1 minus T cold 1. So I have two differences. One is this, the other is this. I just subtract them and I just divide both of them and I take the logarithm. And you can call this, oops. You can call this delta T2, the temperature difference in the outlet. And this is the temperature difference in the inlet. So this is also temperature difference in the outlet, and this is temperature difference in the inlet, right? You can simplify it to have Q is equal to UA delta T2 minus delta T1 divided by logarithm of delta T2 over delta T1. Voila. Okay. So where delta T2 is the difference in outlet temperatures. Positive. And delta T1 is the difference in inlet temperatures. Okay, and you can actually give this a name. Okay, delta T2 minus delta T1 divided by logarithm of delta T2 divided by delta T1. This is the log mean temperature difference, very important quantity in heat exchanger design. Log mean temperature difference, or sometimes some resources show it as delta T LM. LM is for log mean. So what did we find? We find that Q is U times A times some delta T, which we call as the log mean temperature difference. So we basically generalize our original formula for temperatures changing over a longitudinal direction, right? And we found the delta TLM for for co-current case, but for a counter current case, a similar analysis would give the following. For a counter current heat exchanger, we get, one would get delta T2 is the temperature difference at one side, which is the T hot 2 minus T cold 1, because wherever the hot is exiting, the cold is entering. That's why we are taking that difference. Okay, delta T1 is equal to T hot 1 minus T cold 2, and both are positive values. Imagine this is the counter current case. Okay, and this is your delta T1, and this is your delta T2. Okay. Okay, so as an exercise to see whether you understood all these analyses, derive the expression for counter current heat exchanger on your own. And the answer, as I said, is this, accompanied by these two things for the counter current. Okay, you should get those for the counter current case. For the co-current case, you have this versus these. Okay. So this is, again, we're in like chapter 22 in textbook.